So I wanted to do a review of a couple. Wow, that was interesting. Try that again. So I wanted to do a review of a couple topics that I noticed some people having difficulty with. The first is the random function. So what I found with the random function is that some people were having confusion as to how to pick the range. Even still, after we've kind of talked about it in class, I'm still noticing some of those second attempts on that one quiz question coming back with the wrong ranges. So again, I want to reiterate what you should be doing to calculate those ranges, or at least to verify that you're correct. Everyone, 45 screens, look up here. Is you should be doing the actual arithmetic to make sure those ranges work. So if I want to get a value between 27 and 86. All right, so now I want to pick out, how do I do my multiplication? What am I going to multiply by? What do I need to add by in order to get my smallest value? So to get my range, the first thing you can start with is just subtracting to find the number of values between 27 and 86. So what's the number of values between 27 and 86? $59? Okay. So you can double check to make sure that you're right. If you add your lowest value to your highest value, right, that should get you to 1 more than 86, if you want to include 86. So if I say inclusive, you have to make sure that you're 1 more than 86, because when you multiply by that 0.9999, it's going to give you 86.999, and when you make it an integer, it's just going to be 86. So you want to make sure that you're getting 1 more than 86 if you're including 86. If you're not including 86, then you could just go up to 86. So if we take 59 plus 27, do we get 86? Yes? Exactly, right? So if I want to be inclusive of 86, I have to multiply by 60. So the range to not include 86 and the range to include 86 are different. And then you could double check your math. Even after all of that, if you've thought your way through it, still go through and double check the math on that and try it out. If I'm looking at 0 less than or equal to x less than less than 1, that's the non-inclusive side. Agreed? The inclusive side would be 0 less than or equal to x less than or equal to 0.999. That's really what it is if we include the end. Agreed? So if I take 59 times 0, I get 0. If I take 59 times 0.99999, that gives me 58.9999-ish, right? Yes? So I'm including up to the 58.999, right? When I'm looking down here. Down here and up here, I'm not including it. So if you're looking at this and you're trying to get to include the 86, this won't work because you're going to lose all those .999s that you actually need to get to the 59. So if you multiply by 60, we get 0 less than or equal to x less than or equal to 59.999. Now we can actually get to the 59 that we need. because the 0.999s are going to go away when we do our integer conversion. Add 27 to both. So that's 27. 58 plus 27 should be 86, right? 0.9999, you sure? It's 85.9999. Make sure you go ahead and do that math. So it's 85. Then we strip off the decimal because we're using the integer function. So it ends up being inclusive from 27 up to 85, inclusive, when we strip off the decimal. But here, when we add 27, we get the 86.9999. When we strip off the decimal, we saw it's going 27 to 86. So really the hard part is this end value. Making sure that you're getting the proper endpoint. And if you have to try it twice to make sure you're getting the right range, then try it twice. Do it once with one value, once with another value. Most times you're off by one. Either you're too high or you're too low. But go through the whole process. Multiply it by the 0.999, add the lowest value, strip off the decimal, make sure you have the two numbers that you're interested in. If you want to go all the way up to 86 inclusive, you have to make sure you end up with an 86.999. If you want to not go up to 86, then it's fine to end up with an 85.999. But you must test out those ranges. You must do the math. The second thing I wanted to talk about and go over that I saw people having issues with was the round-off error. That's the next math piece. The biggest issue I saw with that is people were just kind of missing the point. When you're dealing with the round-off error, you never want to go back to changing it to a double. You do not want to restore your value as a double ever. I saw several people, and it probably worked in their code the way they ended up doing it, but I saw several people change it from a double into an int by doing their multiplication, moving the decimal, using the math.round. That was great. And then they go ahead and they do some calculations and they store it as a double again. You just reintroduced the same error that you eliminated. Once you've converted it to an int, do not go back to a double. Java does not handle mathematics with doubles perfectly. It has that issue with the round-off error. So what actually happens is I could either have 35.999 or 36.000004. Java looks at them both as 36. However, if you do a casting of an int on this, you're going to get 35. If you do a casting of an int on this, you're going to get 36. That's why we have to use the math.round function. Just doing a casting will get you rid of the round-off error half the time, but not all of the time. So you have to use the math.round. You had a question?
Is it okay if we turn it into a double in order to show the total change?
No. Don't store it as a double. You can print a double. And I'll show you what I mean by that. But you're not restoring it as a double. You're just printing it as a double. So when we do our conversion, if I wanted to do take some type of calculation, or let's just take one of these numbers. and convert this, I would do a math dot round and then times 100. Or you could do times 100 and then math dot round. Either way, it's going to end up kicking over. If you do multiply by 100, you get 35,999. Math dot round will kick it over to 3,600. If you multiply by 100, math dot round clearly kicks it over to 3,600. So either way it'll work. You can either do it before or after, but you do a math dot round on the double. Multiplying by 100, or how many ever decimals you want to go to, but usually 100 where we're talking about, because we're talking about money, will give you the value in pennies if you're thinking about money. So we have now, and this stored as an int when we cast it as an int. So yes, you still have to cast it as an int. If you do math.round of 36,004 then times 100, you still have a double. And any calculations that you do on that will still be subject to round-off error. Doing all the math.round and then storing it as a double, again, you did nothing. You did not solve the problem. The problem is the fact that it's a double. So we have to make sure we no longer represent this as a double. So what we have stored in memory now when we do this is 3,600. Not 0.0, just 3,600. It's an int. Any calculations we do on this now must involve integer calculations. Integer division. All of that. Yeah. You could do it either. I mean, why does it calculate the times 100 before the math round? The functions come as a set of parentheses. Kind of like if you do a square root of 26, you would calculate the square root first before you did any multiplication. Think of it kind of like exponents. I know it doesn't fit in the PEMDAS because we don't have functions like this in regular math class. But any functions would be done first, and then multiplication. But like I said, it doesn't really matter. The result's going to be the same. So it's kind of like order of operations, multiplication being the same level as division. If you do round and then times 100, it's going to be the same as times 100 then round. It's not going to make a difference. It's going to give you the same answer. Does that make sense? Okay. So in the box we get 3,600. Now we can do all of our math. Subtracting, adding, whatever we want. As long as it's all integers. Never should the word double approach here, again, unless you want to print out a decimal. If you want to print out a decimal, you're not going to store anything as a double. You're going to use a casting. So if I wanted to print 3,600 as a double decimal, so 36.00, let's say. Or let's say we did some math and we got it to be 3526. So we did some subtraction. Well, we're going to now take this, divide it by our 100. But we have to be careful when we divide it by 100, because integer division divided by 100 is not going to give us what we want. Integer division divided by 100, it's going to throw away the decimal. So what we really want to do is cast this 3526 as a double, then divide it by 100. But it's a casting. We're not storing it inside of a double. You also have to be careful of your parentheses here. So if I do double 3526 divided by 100, the casting will happen first. This now becomes a double. We divide it by 100, and the result is 35.26. But you don't want to store that number anywhere to do math on it, because if you do that, now you're back to round-off error. You have a double stored again. Any calculations you do on that double are, again, subject to round-off error. Will you see it with every calculation? No, and that's the problem. If it was something that you saw with every single calculation, we would not be talking about the disasters that happened. It should not be something that is obvious. You could run 100,000 calculations and never see a round-off error. That doesn't mean you won't get one when it really counts. You know that 1 in a million shot? Well, you only tested 100,000 times. You know? So, yeah, it's possible that you get the round-off error and you won't ever see it. So when I'm looking to see if you've accounted for round-off error, I'm looking at your code. I'm not throwing in numbers. I'm looking in to see that you properly handled the doubles as ints and did all that. You could show me any data that you want. Say, hey, Mr. McLaughlin, I did all these numbers and I never got a round-off error. That's fantastic, but that doesn't mean you won't. 1 in a million shot. Show me 1,000,000 pieces of data and then maybe I'll believe you. Maybe. Most likely I still won't. I'll still look at it and go, nope, that's not right. So when we convert this way, we get this. If you do this by mistake, and this is where some of you are getting weird answers. In this, the integer division happens first. So we're not going to get the answer we expect. 3526 divided by 100 in integer division is 35. Make it a double. And you get 35.00, which is, some of you were noticing that, and you might have noticed that in your change machine. If you're doing it improperly, and you go to print out the change, you're getting 0.0 change. That's why. Your parentheses are in the wrong spot. Parentheses get done first. So if you put all of your division in parentheses, it becomes integer division. It's an integer divided by an integer. It's going to do integer division. It's going to throw out the decimal. You don't want integer division in that case. You want a decimal. That's what you're trying to get. Trying to display it as a decimal. So you do that calculation by casting it as a double first. So this is right, this is wrong. But Java has this uncanny ability to let you screw up. It will allow you to do things your way because it's meant to be a flexible language. It's not designed to make judgments about the way you're writing code. It will let you write code any way you see fit. Other languages won't let you do stuff like that. More restrictive languages will just say no. Some languages don't even have doubles. They just use all integer math by converting everything behind the scenes. Look at your calculator. Your calculator will not have a round-off error. The way it does the calculations. It keeps that from happening. It automatically rounds all of your answers. You might see 35.99999 on your calculator, but that's not what the calculator sees. The calculator is actually doing this up here behind the scenes and then displaying it on your computer. It's doing that math.round. So it avoids the round-off error. Just never shows it to you. Makes sense, right? They programmed it. You wouldn't want a 5th grader having to deal with round-off error. That'd be bizarre. Math is hard enough at 5th grade. Instead of saying, hey, yeah, 35.0004, yeah, that's really not, that 0.004 doesn't really mean anything. Having a hard enough time helping you guys understand that, let alone a 5th grader. So calculators, they work fine. Java, nope. Java just gives you whatever the raw function is and nothing else. It doesn't pretty it up. So those are the two that I had in mind. Is there anything else out of the things that we've been working on that anybody's been struggling with that you want to talk about? I mean, I know we've played with modular math, and I think everybody's okay with that. If you're not okay with that, I just sit with a calculator and start playing with it. Try some values to see what you can get. Some of you were not convinced that modular math was the best way to solve the change machine problem. and did like this really long, complicated way of adding and subtracting. No, I want you to do it with modular math. It truly is the best way of solving it. So if you did the change machine problem and already submitted it, and you did not use modular math to do it, it's going to be coming back to you, just so you know. And you'll have to resubmit it. Modular math is the way to go for that. It's simpler. In addition, the goal of the lesson was for you to learn some of these new math functions and how to operate in computer science. Yes?
When you're doing the math out round, is the times 100 going to be inside
You could do it either way. It doesn't, if you think about it, why would it? You know, think about it. Let's do the quick arithmetic on that. If I have 35.999, multiply by 100. Round it. It's 3,600. Right? If I round it first, $36.000, multiply by 100, $3,600.000. This is actually 0.000. Until we cast it as an int, right? And then we cast it as an int, we throw away the zeros, and now we're just pennies. So which order does Java do it in? I would suspect it does the math.round first if you put that in parentheses. But honestly, I don't know, because I don't have a good way of testing that. You know, because the answer comes out the same either way. There's really no great way of testing that. It's kind of looking at it as if you do PEMDAS order left to right for addition and subtraction, or if you just do add up minus and make everything addition. It comes up to the same thing. There's really no way of telling how you did that answer. So suppose I had a price of $29.87 and I paid with $30. Actually, let's do $29.07. Gives us more options. And I pay with $30, right? I'd want to do that conversion process that we just talked about it and make this 30 with 2 zeros, so 3,000, and make this 2907. Then I subtract. Round off error is gone. I'm dealing with this just as straight as ints. Subtract, and since I told you you can just deal with the dollar difference, I'm not doing the challenge version, I'm just doing the version that's required. When we subtract, we get 93. And now I got to see how many quarters are in it, right? We're going to start with quarters. Well, if I do 93 25, I get 3. Well, that's nice. That's how many quarters there are. And now if I want to get how much change is left over. Well, that's 93 mod 25. And then I do it again. Only this time I'm not using 25, I'm doing 10. So 93 mod 25, that's 75 minus 93. $18. Thanks. Just want to make sure like people are listening. I mean, Nils is asleep, but so 18 divide 10 is 1. Dimes. Done. 18 mod 10 is 8 pennies. Done. So much easier than some of the math I saw you guys trying to pull off. Right? How many people did this with like this really big, long, complicated function where they're adding and subtracting and multiplying and then going back up and then subtracting. Trust me when I tell you things. Modular math is the way to go with that.